Muy bien, y la última presentación de la noche va a tener una presentación bastante especial que estará a cargo de nuestro director, el doctor Carlos Zavala. Doctor Zavala.
Sí, muy buenas noches, ¿no? Es para mí todo un honor presentar a mi compañero de carpeta, al doctor Koichi Kusunoki, ¿no? Cuando vemos ahí la torre de la Universidad de Tokio, que me trae grandes recuerdos, ¿no? Y también está con nosotros mi senpai, ¿no? Mi buen amigo Oscar López, ¿no? Que también estudió en la Universidad de Tokio. Debe traerte también grandes recuerdos ver esa foto,
Así
¿no?
es.
Así es, cuando comíamos en el comedor, ¿te acuerdas? Ahí en el sótano, ¿no? O al fondo, ¿no? Al fondo, el fondo era mejor, recuerdo, el que estaba al lado del hospital. Ok, bien, bueno, esas memorias que tenemos. Bien, permítanme entonces en esta noche, ¿no? Presentar al doctor Koichi Kusunoki, ¿no? Quien es profesor en la Universidad de Tokio, ¿no? Con quienes recientemente hemos firmado un convenio para realizar un proyecto de cooperación conjunta bajo el esquema de cooperación SATREPS, ¿no? Y vamos a desarrollar un sistema experto en el cual van a trabajar todos los grupos del SISMIT de investigación. Asimismo van a trabajar todos los grupos de las diferentes instituciones encargadas de los desastres naturales, como SINDESI, CENEPRED, ¿no? Algunas universidades locales que han tenido a bien a responder nuestros correos de invitación, ¿no? Y asimismo, debo de comunicar que gracias a este proyecto, muchos de nuestros alumnos y profesores van a poder intercambiar conocimiento con los profesores del Japón. Y eso es algo que puedo decir y reconocer, ¿no? Públicamente. Lo hemos logrado en conjunto con el profesor Kusunoki, ¿no? Luego de postular, how many times we submit to GST and JICA? 4 times, I think so.
Yeah.
Or 3 times. ¿No?
To Peru?
No, for success on SATREPS.
4 times, 5
4 times, ¿no? Yes, that's right, ¿no? Nosotros aplicamos 4 veces a este proyecto y recién después de 4 veces hemos tenido éxito. Entonces, como quien dice, hay que perseverar para poder ganar. ¿Ok? Y bien, entonces, esta noche el doctor Kusunoki nos va a presentar una ponencia bastante especial, pues muestra el comportamiento estructural, ¿no? que es característico, vamos a decir así, ¿no? De una estructura monitoreada. ¿Okay? Es decir, va a poder presentarse, ¿no? En esta noche, ¿no? Un edificio de 5 pisos que fue ensayado en eDefense, ¿no? Y que gracias a este comportamiento, ¿no? Estructural que incluye el monitoreo con sensores, ¿no? Se ha aprendido muchísimo, ¿no? Pues esa escala natural. ¿Okay? Entonces, sin más preámbulos, presento al doctor Koichi Kusunoki, ¿no? Quien nos va a dar la ponencia en inglés, ¿no? O ya lo puede dar en castellano, no lo sé, ¿okay? Pero lo invitamos entonces adelante, el auditorio es suyo. Oh, please, go ahead, you can open your transmission. Thank you.
Okay. May I share my presentation file?
Yes, please, you can start. Okay.
Okay, Professor Zavala, thank you very much for your kind introduction. So, buenas tardes. ¿Cómo está usted? yo soy Koichi Kusunoki de Japón. Yo estudio español, but that's all what I can speak in Spanish. I'm sorry, but I would like to give my presentation in English. So before starting my presentation, as Professor Sabara introduced, we are going to start a new SATREPS international cooperation project with SISMIT. And we tried, like Sabara-san said, we tried 5 times probably. I don't remember exactly. That's because our new SATREPS project is the first project which is approved for second term under the SATREPS project. The first SATREPS project between Peru was approved as the first SATREPS project. So this is also the first SATREPS project for the second term between Peru and Japan. But today, the topic is a little bit different from the SATREPS project, but the research contents will be applied for the SATREPS project as well. So today I would like to talk about the E-defense test with 5-story full-scale reinforced concrete structure. E-defense is a shaking table facility located in Kobe. So it is the biggest shaking table in the world. So let's get started. So this is the history of the earthquakes, major earthquakes hitting Japan, and the history of the seismic codes. We developed our first code in 1919. It's called Urban Building Law. Then you may remember that in 1995, the pretty big Kobe earthquake hit the mega city of Kobe. Then so many buildings collapsed due to the shaking. But when we investigate the damaged area, we found that the current building code worked very well. Only the old buildings designed according to the previous seismic codes collapsed. So that's why we didn't amend our building code due to Kobe earthquake. But in year of 2000, we added another option for the structural calculation, which is called the capacity spectral method, which can predict the response of the structure explicitly for structural design. Okay, this is the basic concept of the capacity spectral method. So we calculate the nonlinear behavior of the structure, then simplify it down to a single degree of freedom system, like this red curve. It's called the performance curve of the structure. Then at the same time, we can calculate the demand curve, which could be the code requirement. So this demand curve shows us how much strength and how much deformability is needed for my building. So usually the demand curve is calculated with 5% damping coefficient, but from this point, yielding point, the structure starts yielding. Then due to yielding, we can expect some additional energy dissipation due to yielding. So the additional energy dissipation can increase the damping effect to the structure. So in such, we can reduce the demand curve according to the yielding factor experienced by the structure, like this. If the structure deform more, we can expect more damping. So here now we can get the reduced demand curve. Then the intersection between the performance curve and the demand curve is the predicted the maximum response point during the main shock or code requirement. Then we can design the structure so that the structure can sustain up to this point. This is the concept of the capacity spectrum method. But here, then we added in year of 2000, but unfortunately, not so many structural engineers applied that option. So one of the reasons is the accuracy of the method itself is not clear. For example, here is a nonlinear model for the member, but somebody will model the member with trilinear model, but another person may model this nonlinear behavior with just bilinear model. Then we can get a different yielding point according to the model you applied. Then if we choose a different model for nonlinear behavior of the members, of course, the nonlinear behavior of the stories can be different according to that of the member. Then finally, if we simplify this nonlinear behavior down to single degree of freedom system, we can get two different second corner points from where we can count the additional damping effect. If the second corner point is evaluated smaller, then we can count the additional damping more. So in this case, the blue model can consider the more damping effect than the red curve. Then the predicted maximum point could be different according to the model which used for the members. That's one of the big problems. So we need to at least check, and if possible, propose a new method to predict the second corner point of the members. And also we need a benchmark test to confirm the accuracy of the capacity spectrum method. So that's why the Ministry of Construction decided to launch a national big project from in year of 2018 for 3 years. Then it's called the Building Standard Provision Promotion Project. Then now Ministry of Construction has a certain budget to conduct this kind of projects every year. Then the number of the project is S30. S means for structural issue. Then the title of the project was a research project on the damping effect evaluation for improving the accuracy of the capacity spectrum method for reinforced concrete structure. It's a quite long name, but anyway, this was the official name of the project. Then the activities of the project is to develop a new function to evaluate the second corner point of the reinforced concrete members. Then we started developing the database of the experimental tests. Then we found that this kind of very deep depths and very narrow width columns cannot be found in the database. But this shape of the column is nowadays quite common in Japan. So we decided to conduct some additional experimental tests with this kind of columns. Then finally, we conducted a large-scale shaking table test on the e-defense, which I would like to talk today. So since the project is quite big, the research group is also quite big. Then the PI from the academic field was Professor Teshigawara, ex-BRI researcher. Then now he got retired from Nagoya University. Then right now he is a professor of Chubu University. Then I'm here. Then the BRI, we have some researchers from BRI as well. Then, because the project itself is quite big, so we asked so many people to join and conduct some other research with the same specimen. Then we decided to instrument some sensors to develop a structural health monitoring system. This subgroup consists of ERI, BRI, and some other private companies. Then we also ask some company to develop an optical fiber measurement system. BRI conducted 3D laser scanning of whole structure and so on. So this is a specimen, almost a full scale. Then, excuse me, the shaking direction is just one way. Then two span direction. Then this Y direction was not shaken. Then two spans, two-bay structure. Then span length was 6 meters. Then this is the elevation. Since we were not planning to shake the specimen in the Y direction, so the span length of the Y direction was quite small. Then we put so many sensors, accelerometers at the center of the specimen, and also the corner of the specimen. And also we applied the laser transducers to measure the interstory drifts, like this. Then this is the plan view. So as I told you, we put several accelerometers at the center of the structure. And also in order to confirm that no torsional response occurred, we put 3 accelerometers at the corner of the specimen, like this. Okay. Then at the center, we can see 3 different accelerometers. One is quite high accurate sensor. Then one is quite low accurate, but quite inexpensive. It costs only the $60 for 3 direction. It's quite cheap. So we put several sensors to confirm what accuracy is required for the structural health monitoring system. Okay. For example, this one, you can see the difference of the sensors. S01, type S01 was provided by the e-defense facility. This could be the highest accuracy, and the measurable range is quite wide. The second one is the intermediate. Then this one is the cheapest. Then you can see the minimum measurable acceleration. It looks quite high. Oh, actually, this one was the best one. You see the accuracy is the highest. Here, but the linearity, non-linearity is a little bit larger than S01. We applied anyway 3 different sensors. So this is the input motion. We decided to input this wave, which is the artificial wave usually applied for the structural design in a practical field. Okay. The phase spectrum was L-central component. Then it lasts, the duration was about 1 minute. So this figure shows the response acceleration of the input motions. The firstly, we inputted 60% of the code requirement to see the behavior in elastic stage. Then we inputted the code requirement level and increased up to 25%. Then we inputted this level again to see what will happen during the possible maximum aftershock. Then after this test, we retrofitted, actually repaired the specimen. Then we shaked again, like this. So we inputted 1, 2, 3, 4, 5, 6, 7 input motions. Here you can see the spectrum of the code requirement. Then for the 100%, the response acceleration agreed reasonably with code requirement. So how to evaluate the damage? We decided to apply exactly the same as the capacity spectrum method, which is the option of the building code and added in the year of 2000. So here you can see the functions to calculate how to simplify down to the single degree of freedom system from the multi-degree of freedom system. That's quite easy function to calculate the response of the single degree of freedom system. I don't want to touch on these functions in details, but anyway, I would like to say the simplification is quite easy. Then with a measured acceleration, we can calculate the capacity curve directly from the measured acceleration, but up to the maximum point, of course. We couldn't measure this region, only up to the maximum response point. So we need to predict the behavior after the maximum point, like this. Then with the mode shape, measured mode shape during the shaking, and the safety limit state previously decided before the test, then we can expect, we can evaluate the damage level of the building like this. In this case, the damage level is evaluated as the level 3. Then during the aftershock, we can predict the response. Then we can also predict the damage level during the possible maximum aftershock, which is assumed to be the same as the main shock. So in order to predict the response during the aftershock, we should develop a new function to evaluate the additional damping effect for the aftershock, like this yellow curve. So for that purpose, we conducted a bunch of numerical simulation, about 50,000 cases to develop the function for the aftershock. Then if the predicted maximum response point exceeds the safety limit state, the system will say unsafe. If the predicted response is before the safety limit state, the system will say your building is safe, even for the aftershock. So in this specimen, the system was installed. We did nothing. The system automatically detected the shaking, then the start calculation, then finally the system shows us the result. Here is I would like to play the movie during the 60% input motion, but I'm afraid that if the internet connection allow me to show this movie smoothly, start shaking? No. Oh, sorry, probably because of the internet connection, the movie doesn't work. It seems just frozen. So unfortunately, I cannot play the movie. So I needed to skip this slide as well. I wanted to show how big the shaking was, but no way. So because of the pandemic situation, actually this shaking table test was conducted in the last December. So then just between the emergency declaration in Japan, because of the pandemic situation, unfortunately, we couldn't invite researchers to observe the shaking table test. That's why the people looking at the specimen is quite few. Yeah. So here you can see, oops. Sorry. So here you can see the 4 different figures. Then for the 60% input motion, 60 to 100 input motion, 60, 100, and 125 input motion, then whole input motions. So the second 125 was assumed as the maximum aftershock. Okay. Then here you can see two curves as a capacity curve. One is the black one. Black one was calculated with transducers, laser transducers installed in the specimen. Then the second one is red curves. They are just calculated only with accelerometers. It's called the structural health monitoring result, because for the actual buildings, it will never be approved by the owners to install the transducers. It's quite obstacle for usage. So for the practical buildings, or for the ordinary buildings, we must do everything with only accelerometers. So we apply some special technique to eliminate the effect of noise. Then here, you can see the difference, how different they are. Then we can say the calculated displacement from the measured acceleration reasonably agreed very well with the transducer result. From the, from the quite elastic range to the very large nonlinear range, the calculated displacement agreed very well. Then after the shaking table test, after the second 125 input motion, the structure was severely damaged, but we decided to repair the specimen by the epoxy injection, like you can see the photos. You see, it took 3 days, but it's a kind of a quite quick repairment. We asked some special company to do that. Then 3 days after the 3 days, we shaked the specimen again. So here you can see the capacity curves, measured capacity curves after the repairment. Then obviously, the initial stiffness degraded, not recovered, not fully recovered, unfortunately. But anyway, you can see the double integral with a wavelet. The wavelet transform is a technique what we used to eliminate the noise component. The structural health monitoring result agreed very well with the laser transducer result. We are confident that our system can be applied for the actual buildings. So this is the effect of repair. The backbone curve of the capacity curves during the 60% input motion. So we expected the specimen remains linear during the 60% input motion. Then you can see the stiffness is about 30% of the original stiffness. So 3 days was not enough to repair the specimen perfectly. So 30% repair is quite low rate, but unfortunately this time 30%. So this is the backbone curve of the capacity curve for all input motions. The black line, it shows the before the repair. Then red curve shows after the repair. Then you see for both conditions, we obtained quite smooth capacity curve successfully. But again, I would like to say that the initial stiffness of after the repair showed quite low to the original condition. So if we calculate the transfer function of the specimen, it's also quite clear that before the repair, the predominant frequency was here during the small input motion, but after the repair, the specimen shifted to here. So that means the stiffness didn't recover fully. But you can see this peak is quite shallow. The width is not so wide. So that means the damping is not so high for even after the repair. So somehow the crack was repaired, filled with injection. So that's why the damping became a little bit smaller, but stiffness didn't come back to the original stiffness. So this figure shows the predicted safety limit state. As I told you, the safety limit state was predicted based on the defined ultimate interstory drift angle, which was 2% for this specimen, and measured mode shape. For example, during the 60% input motion, the maximum response point was around here, somewhere around here, here. No, sorry. Yes, here. Then we couldn't predict how specimen will go after this point because there is no measured data. So we decided to just maintain the maximum response horizontally, so, because we don't know how much strength will increase. So we decided to go horizontally. Then the extrapolate the capacity curve up to the until when one of the stories reach the 2% drift angle. Then these red circular points are the predicted safety limit state. So you see, even the very elastic small input motion, of course, the strength was estimated too small because there was no shaking after this point. However, the predicted displacement at the safety limit state agreed quite very well with other input motions. So for the much stronger input motion, of course, the specimen entered the nonlinear region. Then finally, the maximum response was quite close to the safety limit state. Then, but the predicted displacements were almost the same. So this is the prediction result. Then during the first 125 input motion, we obtained the black capacity curve here. You can see. Then we modeled this a smooth capacity curve to the trilinear model like this, blue trilinear model. Then we estimated the safety limit state here and the safety limit state here. So fortunately, the maximum response didn't exceed the safety limit state. So damage level was evaluated level 4 because it's before the safety limit state. But during with the estimated or predicted demand curve for aftershock, which is here and here, the predicted maximum response point during the aftershock, that means if we input the 125% input motion again, the system predicted the maximum predicted displacement is here or here for the negative direction. So it obviously exceeds the safety limit state. Then the system recommended not to input the 125%. The structure will collapse. Then we input it. Then here is the maximum point. Then for the positive direction, the maximum displacement for the second input was smaller than the first input because the whole specimen shifted to the negative direction. Then the maximum response in the negative direction was here. So fortunately, the specimen was standing, but we we can say that our system predicted for the safer side. So probably the time is almost over. So I would like to go quickly. So nowadays we have the damage classification method as a standard in Japan, but it's based on the visual inspection. Okay. And also earthquake insurance system we have. So for this insurance system, inspector will visit your building to evaluate the damage of your structure. Then they will decide how much premium will be paid according to the damage. So, for example, this insurance system was developed after the 1964 Niigata earthquake. Then the ceiling, because this insurance is funded by the central government, so government set the ceiling amount. So, but the amount is quite a huge amount. But anyway, the government will not pay more than this amount. Then the way to evaluate the damage is quite similar, but a little bit different from the damage classification. Both are based on the visual inspection. Then I would like to skip. Then for our specimen, we asked some inspector for the earthquake insurance to come and do the inspection with our specimen. And also, we also conducted the damage classification based on the standard, which is a visual inspection. Then now you can see the three different methods: structure health monitoring, then ordinary damage classification, and earthquake insurance. So you can see the three different methods gave us almost the same damage classes. So they agreed reasonably well. For the 60% input motion, since we didn't stop the hydraulic oil pump system, it's not allowed to get closer to the specimen. So that's why the visual inspection was not conducted after the 60% input motion. But of course, with structure health monitoring system, then the damage can be evaluated automatically without any visual inspection. This is the result during after the repairment specimen. So we shaked the specimen in just one day. So we could conduct a visual inspection only after the shaking, so for this point, but all methods says the collapse or severely damaged. So again, the evaluated the damage levels agreed very well among the three different methods. So this is the conclusion. Large-scale shaking table test was conducted successfully, always stressful when we conduct such a big shaking test, but fortunately we succeeded. Then the capacity curves can be derived from the measured acceleration. Then safety limit state can be predicted with the defined interstory drift angle. And also the damage level during the aftershock can be predicted safely, and the evaluation result agreed very well with conventional visual inspection-based evaluation methods. Thank you very much for your kind attention. That's all for my presentation.